Perhaps one of the more noteworthy retro titles in the modern era of the internet is Dr. Jekyll and Mr. Hyde for the NES. Is the game fun? Well, the concept behind this game is brilliant. Jekyll must walk to the right to arrive at church and get married. He encounters townspeople, birds, and insects along the way that prevent him from making progress. His goal along this journey is to avoid conflict. The game uses two meters. One is your typical life meter that represents your health. Lose all your health and you die. The second is a stress meter. When this meter depletes, you turn from Jekyll into Hyde. As Hyde, you move to the left and can now attack in multiple ways, by punching and by using your Psycho Wave. As you eliminate enemies, your stress meter moves from H back to J. Reach this point to turn back into Jekyll, receive a health refill, and resume your rightward movement. The genius of the game's design comes in its method of representing humanity's internal struggle between good and evil by way of a video game, and it finds its release in a pioneering era for genres. Jekyll moves to the right, toward good, and Hyde moves to the left, toward evil. Hyde's stage is a mirrored version of Jekyll's stage. If, as Hyde, you manage to progress as far as you did as Jekyll, evil surpasses good and therefore wins. Lightning strikes and the game is over. Now, we can talk about concepts of game design all we want and give out an award on that front, but the game loses momentum as we move from concept to execution to gameplay. Every game must eventually answer the question, is it fun to play? But that's not why I am here. I'm here to answer the question, is it fun to dissect? Oh yes. Among the enemies that Jekyll encounters is the Bomb Maniac, a rather dapper-looking fellow who plants bombs in town to ruin your day. He places it and runs away. The fuse lights, the bomb explodes, and the damage and stress cover a wide range as you attempt to run away at a blistering speed of about 24 pixels per second. To analyze this, we need to talk about object locations and collision detection. This game uses a method for object handling unlike most that we've encountered in this video series so far. Whereas a typical game may have coordinates for an object, apply physics to those coordinates, and then create the sprites to illustrate said object on the screen each frame, Jekyll and Hyde leans heavily upon the sprites themselves for the application of logic. In this example of Jekyll's gameplay, his sprites and OAM are very specifically slotted into this area here. Head, chest, waist, legs. They remain locked in this order and are often referenced directly in code as their addresses are known. When you move Jekyll from here to here, the logic double increments the X coordinate of each of his sprites in RAM in order to move him. Those values are moved from RAM to OEM at the appropriate time between frames, and they therefore appear to move on screen after the next frame has been drawn, thanks to those incremented X coordinates. So now that we know logic is sprite-based, so to speak, let's return to the Bomberman scenario. The size of the bomb, sit down if you aren't already. The size of the bomb's explosion from the XY coordinate of the 8x8 bomb sprite is 60 pixels to the left, 50 pixels to the right, 48 pixels up, and 48 pixels down, encompassing an area of about this. Running away at a rate of 2 pixels every 5 frames, or 24 pixels per second, gives you just enough time to yell "no" as you try to avoid the explosion. It is rather interesting that the game deliberately uses different horizontal distances from the bomb's coordinates to designate the explosion's range. It's possible that these values were reversed in the logic. If they had been 50 and 60 respectively, the bomb would be closer to the center of the explosion. But then again, collision detection is based on specific Jekyll sprite location, and perhaps the explosion's dimensions are tailored to that, as well as the goal of rightward progression. Jekyll is composed of 8 sprites. For the bomb's explosion, the bomb sprite's coordinates have 3 distance checks performed against the horizontal distance from the bomb to Jekyll's shoulder, as well as from the bomb to Jekyll's chest. There is also a vertical distance check from the bomb to Jekyll's shoulder. If any of these checks fall outside of the specified range, Jekyll does not take damage. I've included the coordinates of the 3 relevant sprites at the top of the screen. When the bomb is placed, the explosion area appears in red. The font color for the 3 relevant checks also turns red if they are within the damage area. If Jekyll manages to get a single one of these 3 locations outside of damage range, that value, as well as the bomb explosion area box, will turn green in color because Jekyll is now safe. In fact, let's manipulate the shoulder sprite's X location in RAM by placing it outside of the explosion range check and see what happens. Even though the majority of Jekyll's sprites are standing right next to the bomb, he's not harmed in the explosion. Now remember that this game is designed around Jekyll moving to the right. That means it doesn't matter if you are to the left or the right of the bomb when it explodes, you will fly to the left when damaged. The game wants to impede your rightward progress. Knockback is therefore always to the left. Collision detection for the bomb's explosion is designed around you facing right. When you face left, you increase the walking distance needed to get your shoulder outside the left side of the explosion area. You either have to walk that coordinate completely out of this boxed area or walk far enough that turning around at the right moment swaps the shoulder and chest X locations such that the shoulder falls outside the blast zone. You can see how the difference in Jekyll's location and direction affect if he takes damage or not via these two screenshots. This detail also explains why you could walk left, turn around to the right, be safely outside the explosion's range, but then turn left, perhaps to deal with another enemy or obstacle, only to take damage from the explosion you thought you already avoided. The simple reason this happened was your shoulder sprite re-entered the blast area before the explosion finished and now has a shorter and therefore inadequate distance from the bomb's location. I've reversed a bulk of the bomb logic and here it is. Pause if you'd like to read through it. We are going to tear it up a bit. Reprogramming Jekyll and Hyde is fun, and there are several ways we can modify the bomb logic to rebalance the explosion size, among other things. Here are the values that define the size of the explosion box. As you can see, they are based on the bomb's coordinates versus specific sprite locations for Jekyll. Since all three have to be within range in order for the explosion to do damage, we skip ahead to increment bomb timer as soon as any of the distance checks fall out of range. First up is a check for 60 pixels to the left of the bomb's X position. Is Jekyll's shoulder sprite within that 60 pixel distance or not? The second check is if his chest sprite is within 50 pixels of the bomb's X position. What if we cut these values in half? Easily accomplished with 2 Game Genie codes. The explosion box is a lot easier to avoid, perhaps too easy, at least when you are playing on an early level, and especially when you only have to avoid a single bomb rather than a bomb alongside multiple enemies. Difficulty ramps up later in the game as bombs are placed at the same time barrels are rolling toward you. What appeared to be too small of an explosion box on level 1 with our modification is actually almost perfectly balanced on level 6. The reason? The fuse uses a different timer depending on what the current level of the game is. Those values are looked up in the ROM, and those times are listed here. As you can see, the duration of the fuse timer decreases the further along you are in the game. You could tweak the first level to have a short fuse similar to the 6th level, or perhaps make the last level's fuse just as long in duration as the first. You could tweak any of the numbers if you'd like. The Japanese version of the game has a fair number of differences from the US release, including the order of levels being rearranged. If we examine the fuse timers from the Japanese game, you'll notice that they use a completely different set of values rather than just being in a different order like the levels. So it would appear that the fuse timers were rebalanced between the different releases. As for the area of the bomb's explosion in the Japanese version, the distance checks appear to be the same. Several other values define various durations of the bomb explosion timeline besides the separate fuse delay. The initial bomb placement waits on that fuse value we looked up. After that, time must pass for the fuse to begin to spark. Then there is time from the start of the sparks to the start of the explosion. Then the kickoff frame to start screen shaking and explosions occurs. This coincides with the start of damage frames. Finally, a single frame check indicates the end of the bomb's explosion. Damage is applied to the stress and life meters starting with the kickoff frame and ending before the end frame. We can modify any of these values, of course. The primary value that we may wish to change is this 1E value, that's 30 in decimal, that signals the end of the bomb's explosion frames. If the screen shake and explosions alongside damage to Jekyll's meters begins on frame 15, how about we end it on frame 16 instead of 30? The result is something that doesn't do much damage to the stress or life meters. We could increase it from 16 to 17 perhaps. Once again, it's about dialing in a value that seems fair. You could certainly increase the duration of the explosion if you wanted. Of course, the explosion duration, size, damage, and knockback distance are balanced together. So if you change one thing, you may wish to tune the other values in order to rebalance. Balancing is a term often used alongside an action RPG or fighting game, but many if not most games have some degree of complexity that creates a give and take relationship between its behind-the-scenes components. Speaking of components, let's talk about Jekyll and Hyde's RNG. The spiders that hang from the trees will move up and down in what seems like no pattern at all. Their movement makes use of the game's RNG routine, and that routine is rather fun. Well, fun if you're a programmer that likes random number generation routines, I suppose. 2 RNG values are maintained in RAM. The RNG subroutine is called to re-roll them. We've examined RNG routines in the past that take a given initial value and continue to perform various operations upon it each frame in order to effectively create a random number. Jekyll and Hyde uses the game's code itself as values for RNG. Let me explain. Jekyll and Hyde is an MMC1 game. It uses the MMC1 mapper chip in order to address up to 128K of ROM, despite the fact that NES is designed around addressing a maximum of 32K. The MMC1 chip works by letting the NES see 2 16K banks of ROM at a time. The upper bank is fixed. The NES will always see ROM bank 7 in the case of Jekyll and Hyde. This is where our RNG routine is stored. The subroutine is always available because this bank never changes. The lower bank, on the other hand, can be switched out depending on which 16K bank the game needs to access. Rather than the RNG subroutine starting with a hard-coded number and then just performing operations on it, it instead looks at ROM values we can currently access in the lower bank and grabs them as part of RNG. The emulator can show us the disassembled code here to the right of the ROM address. Instructions, addresses, values, they are written out in 6502 assembly. However, in the ROM itself, they are stored as bytes, of course. CD, 83 hex, 07, and so on. Numbers are numbers. Let's just use the bytes that represent code and data as RNG values. Operations are still performed to add some degree of randomness. Each value pulled from the ROM is added to the previous RNG value. We maintain a counter in RAM so we make sure to get the next number in the ROM each time. On top of all of this, remember that the bank can be switched, so we may end up in the RNG routine and reference code and data from bank 6 for our random number, or maybe we're looking at bank 5 at the time and grab our value from there. The sheer volume of bytes available spread across multiple banks of code and data that are swapped at various times and added to whatever the old RNG value was helps keep RNG fresh in the game. It also means that, unless I'm mistaken, waiting to find a pattern for the spiders is a waste of time. Once again, the game gives us a lesson in patience while playing as Jekyll. Maybe we're tired of patience with Jekyll and Hyde, so how about we reprogram the game just for fun? Let's double Jekyll's walking speed from 2 pixels to 4 pixels per position update. This is going to require more than just a couple of Game Genie codes. First, a little background behind how the game works. We need some perspective on the implementation of walking and scrolling. There are 2 primary methods in the game logic for moving Jekyll to the right. If he's located to the left of this column, his sprite's X positions are incremented twice, that's 2 pixels, to move him to the right on the screen when the player presses right on the D-pad. We literally move the sprite locations on the screen. When he reaches this column, the sprite's X positions are no longer incremented. He stays in place relative to the television, and the level itself moves. The background, the objects, the enemies, they move to the left to make it appear that Jekyll is moving to the right. These are just some typical implementations for a side-scroller. Now, Jekyll and Hyde is very much designed around knowing exactly how many pixels he moves at a time, and that number is 2. In addition to that, he does not move on every frame of the game. So if we increase that movement for these 2 instances of movement implementation, the game needs compensation across the board in order to function properly. I'm going to reprogram this logic enough so that he moves faster when walking on the left side of the screen and when scrolling the screen, and I'll also increase the leftward movement for objects and enemies during scrolling so they move with the level. If I didn't do that, it would look like they were on a treadmill as the level is scrolling. We'll break a lot of things, but there should be enough of a change for entertainment purposes. This is the most reprogramming work I've done for Behind the Code so far. Let me talk you through it. This is the original code. Here's a quick breakdown of how it works. This top section checks Jekyll's shoulder sprite's X position to see if it has reached the appropriate column for scrolling. This determines if we scroll or if we move Jekyll's X positions for his sprites. Speaking of which, the next section below contains code that loops through each of the Jekyll sprite's X positions and increments them twice in order to move him 2 pixels to the right. Inc is a useful operation because it takes the value at a specified location, adds 1 to it, and stores it using a single instruction. Since we need to add 2 to each of the expositions, programming elected to include 2 ink instructions for each. Alternatively, we need to leave his sprites where they are on screen and scroll the level. This section handles changing the camera position values for scrolling the screen. The actual PPU scrolling logic uses them later. The same method is applied to a few other values. It's a common theme throughout the game's code. Move this 1 pixel. Okay, now move it again 1 pixel. This subroutine here, D7A7, performs several operations including moving the enemies and objects 1 pixel to the left. We need to move them 2 pixels per update, so the subroutine is called twice, back to back. Jekyll's X location update for his sprites and camera scrolling need to have their movement logic changed from a pair of increment instructions to your typical ADC-based addition. This gives us flexibility for how many pixels we move him at a time. Enemy and object movement to the left is performed using decrement or DEC instructions inside that D7A7 subroutine. Now we could change these decrement instructions to a subtraction similar to our addition change that we have planned. However, I did not reverse engineer that entire subroutine. So for objects and enemies, we will take a brute force approach to moving them 4 pixels by calling the subroutine 4 times. This method of programming is what we call absolutely terrible. This is not an endeavor for the game genie. With that said, here's the replacement code. Pause the video if you'd like to compare and contrast. I have a few notes to share. There are several no operation or NOP instructions due to the volume of code that was removed versus changed. When you edit assembly code in this emulator, the labels remain tied to their associated ROM address regardless of your changes. So when you add or remove lines of code, the code's ROM addresses will change, but destination and label ROM addresses will not. In short, there are a lot of manual changes to make for branching, jumping, and labels. I already changed the addresses by hand once and didn't want to do it again thanks to additional edits as I continued to reprogram. The code ended up all over the place and is a mess, but it's also enough to showcase a change. And so, here we go. He certainly moves a lot faster. This change definitely decreases the difficulty level. Jekyll appears to be training for Super Mario Bros. In fact, speaking of Mario, perhaps a run mechanic would have been useful in this game. What if Jekyll is his normal slow self, but you could hold the B button to run for a limited amount of time? Perhaps you have a run meter that takes time to recharge, so you'd want to be selective as to whether you sprint or conserve energy depending on obstacles faced. Jekyll can perform a cane attack by pressing the B button, and it's only useful against bees. Perhaps this component could be removed, so pressing B to start a run would mean the player doesn't have to wait on the cane attack to happen first. The attack is arguably useless anyway. Just a few thoughts. I feel like this game fell short of its potential. Changes such as increasing Jekyll's walking speed like we've done, or adding run functionality pretty much require the game to be rebalanced, and we did not do that at all. As an example, environmental collision detection broke in a rather interesting way. Whenever you reach an area where you need to jump up to a higher level, running into the step instead of jumping on top of it will warp you to the next level. Oops. Our walk cycle still functions well enough, but the 4-pixel based scrolling is rather jerky. However, if we don't care about jerky scrolling, we might as well increase the pixel change from 4 pixels per update to 8 pixels per update. Now we're moving. This likely breaks additional things. If we were to increase movement even more than 8 pixels at a time, we may start to outrun the background tile load routines and end up with garbage graphics among other potential problems. Alright, that's enough. Like and subscribe for more videos like this one. Leave a comment regarding what you would reprogram in Jekyll and Hyde. I have a Patreon available if you are interested, and thanks for watching.